Gravitation and planets. Of course, when we talk about gravitation, we talk about planets, and there is a gravitational field around the Earth and around all the planets in the solar system or in the universe. That's the way we understand it today. Doesn't necessarily mean still true tomorrow and the future, but that's what we have so far, and it is explaining many phenomena happening in the universe. It is succeeding in that in a good accuracy. Now, man been recently sending spacecrafts to the space. Those spacecrafts are being launched through rocket technologies to the outer space. Scientists came out with better ideas on how to reduce the amount of energy consumed by those spacecrafts in order to reach farther in the universe. Let's say we want to go to Mercury, or we want to go to another solar system in the universe. We need to reduce the amount of energy used during launch and during directions. So scientists came out with a bright idea of being able to let those spacecrafts use the gravity of the planets that they are passing by, so that they can pass in the gravitational field of that planet that is moving in the same direction of curvature as the spacecraft, so that it will give him a gravitational boost for the spacecraft, and it can go even further than it was anticipated. So you can see here, Voyager 1 passed Jupiter gravitational field and Saturn gravitational field, and Voyager 2 passed Jupiter and Saturn, Uranus and Neptune in 1989 to be able to reach its final planned anticipated destination. So that's something to keep in mind. We use something called gravitational boost, or planetary gravitational assist, or gravity assist as some people call it. Each time the probe or the spacecraft gets near enough to one of these planets, the gravitational field of the planet causes the path of the probe to curve, and the planet would deflect the space probe, and if the planet is moving in the same direction as the probe, the speed of the probe after its planetary encounter will increase. So in this case, we're using the gravitational force exerted by a body in the space, as they call it celestial body, to reduce interplanetary travel time, and we call that as gravity assist. So we can see in this graph that the spaceship or the probe Voyager 1 passed close to Io, Ganymede and Callisto. Those are Jupiter's moons, and all of them having gravitational fields as well that helped Voyager to head way farther in its mission and with less energy consumed. Now, if you want to talk about the gravitational field versus gravitational force, the acceleration due to gravity near or on the Earth's surface is 9.8 downwards. If we want to explain where did the 9.8 come from, we can see here we have forces acting on a test mass m test, and we have distance, and we have here the mass of Earth as the m source. The only force acting on m test is the gravitational force exerted by Earth on the test mass. Now, the magnitude of the gravitational force can be found in two ways, either using the concept of weight or using Newton's law of gravitation. Using the concept of weight, the F G equals the m test by g. Using Newton's law of gravitation, you have the gravitational constant by the m test by the m source over the distance squared. Since the value of Fg is the same, doesn't matter which equation you use, so we can set both equations to equal each other. That would give you g equals the gravitational constant capital G multiplied by m source over the distance squared. So it doesn't matter where the test mass is located in the universe, you can calculate the magnitude of gravitational field strength or gravitational acceleration at any distance from a planetary body if you know the mass of that body and the separation distance between the center of the test mass and the planetary body.